In this video I wanted to show work in progress on tool that I'm working on, which allows you to instantiate objects along the curve based on the curve's angles between its points. So I have set up a quick demonstration of this tool, and I wanted to showcase how it works and walk you through this network and how it actually is set up. And if you want to get this zip file that I'm demonstrating, you can download it from the description below. So let me show how this tool works. So the tool supports open and closed curves. We basically have to provide a curve that we want to instantiate our geometry to, and we have to provide the library of instantiated corner pieces that we want to copy to those pieces. And let me show how the tool works. So let's say I'm instantiating this one, and let's say I want to expand this node, expand this network of pipes. Just select this curve and start drawing out another curve, and you can see, since everything inside here is instantiated, you can see that it's super fast, and we can move it whatever the way we want. It's going to find the correct piece to instantiate over, and it's going to create these straight pieces. The tool works very nicely. And so this is with the pipes, and I have another example with the so in this demonstration with the pipes we have a 5-degree increment. So you can see that in this library that I'm providing, my angles are from 5 degrees to 175 degrees. So I can instantiate those angles. And I have another example where I have a 30-degree increment. So let me change to the snap angle of the tool to 1 to 30 degrees. Let me show this one. So in this case, I have only 5 input geometry that I have manually set up offset to. You can see that I have only I only five pieces that I am instantiating along the corners. And what's cool about this tool, that it's going to automatically snap to the angle, to the closest angle that we are providing our snap angle to. So since we have only 30, 60, 90, 120 and 150 degrees, we want to make our snap angle to the 30 degrees so that it's going to snap to the closest angle that divides by 30 without the fraction. If you take a look at how tool deals with this one, so you can see that we have instantiated the geometry and it has also correctly selected this. And the input curve is this one. You can see the input curve is not really, it's impossible for us to draw it manually precise angles. But with this tool, what you can do is, as long as you're reasonable about it, it's going to automatically go ahead and snap to the closest angle, and we can go ahead and play around with it. You can see it's going to try to find the closest 30 degrees, and the curve is going to follow the general shape of it. So the 30 degrees is pretty big margin between the corners, so it would be better if you had some like maybe 10-degree increments, but something like this works pretty well as long as you are reasonable about your input curves. And to show how it works underneath, I want to quickly walk you through this network. So let me go back to the snap angle of 5. So now you can see right now I have there are a couple of copies that are snapped to the 30-degree increments, but we have to provide geometry for each corner. So for this one I want to go back to my pipes, where my pipes are actually set up with the 5-degree increments. So right now I am snapping to every 5 degrees, and I have set up my pipes here with the correct angles. So let me go through the, first of all, first part of this network is snapping to the snapping of the angles. So in this first part, you can see I am setting the angle. So once we are done with this part of the network, we have set up our curve angles attribute. And this attribute is being used as a piece attribute when copying geometry on these points. So let me go through this network. So first of all, I want to go ahead and maybe add let me provide it a simpler polycurve with just one angle polycurve, something like this. And I'm going to make it something like a 80-degree curve. like this and make my snapping to 45 degrees. So that I know that, let's say I want to snap this to the 45 degree increment, so the closest increment would be a 90 degree. So the network, you can see after all the network has done, it's going to go ahead and snap it to the 90 degrees. And let me go to the single pass to show the difference. So you can see input curve is this, and this attribute triangle is snapping to the 90 degrees. So let's go through this input network. So first of all, we do a for each primitive loop. We remove any inline points that we might have. We sort by vertex to make sure that the point count is not random, something like a 0, 1, 2, not like a 0, 2, 1. We need our points to be in order of the vertices. And then we want to go ahead and initialize attributes. So the copy attributes that Houdini utilizes is normal and up vector. And then we also need our tangent. That's going to be a vector that's going to rotate around for the angle adjustment. And we have our edit PT attribute, which is the total which tool supports closed and open curves. And in some operations, like for open curves, we do not want to try to measure angles for the last and first point, because there's really no angle to measure. So we basically say if this is an open curve, we say we do not want to edit this point, and this by default this is set to 1, so that means that this is set to edit this PT. But we basically check if this the number of vertices of the input geometry is not equal vertices. So that means that when the curve is closed, there is an extra vertex on that geometry. So that means the geometry is closed, and we want to generate angles for all of them. But if this is not closed, we want to basically go ahead and unset edit PT for the first and the last point, and this is done with this switch node. Then we set our normal attribute. As you see, the normal attribute is basically just pointing is continuously points to the previous segment of the curve outwards, and then the up vector is pointing to the next segment of the polycurve. So this is going to affect the instant geometry rotation. And then we also get our tangent, which is going to be used for rotation of the point, as an axis for rotation of the point, to adjust to the 90 degrees. And then we also get our degrees, and the degrees are basically just the dot product of the normal and up vector, and we use a cosine on that dot product and set it as an attribute, and you can see the angle is being set up as 85 degrees, and angle is being calculated from the normal attribute to the up attribute, and the angle snapping happens inside here. Let me open this up. We're basically getting our snap angle, which is set up as a parameter inside here. We check which angle is going to be closest to. So we do not want to try to snap to the angle like 45 degrees, which would be too much of a. So the closest one would be 90 degrees. We check which rotation to the basically which rotation is the closest to 45 or 90 degrees to the closest angle that would divide with 45 degrees without a fraction. We basically get the smallest amount of rotation we need to snap to that angle, and we go ahead and rotate it using a quaternion. We basically rotate the next point using the quaternion and set its position. That's pretty much it. We have snapped our point. So I'm not really all that well, I can't really explain all that well this quaternion, but it's pretty explanatory when you take a look at it. I have tried to annotate the best I can. But we have basically just snapped this point, and in this feedback loop we are iterating over every point of this geometry, and basically we are doing this feedback each iteration. So in the next iteration we are feeding back this adjusted geometry and doing the next point. So if we had another polycurve like here, the current point would be 2, and we would adjust the point number 3 angle. And we're just doing it for all of them, and after the end of it, we are cleaning up, we are removing any inline points that might have been created from the snapping of angles. And then we go ahead and set the normal and tangent and up vector one last time because of this removal of inline points. There could be a chance that we have removed some points, so just to make sure, we are copying basically these two same nodes to set angle one last time. And after that, we are setting the attribute closest to the snap angle one last time to make sure that so there could be like a chance that the angle has not been completely snapped to that angle because of the precision issues when we are iterating through it. So without the rotation of the actual points, we want to go ahead and set this attribute to the closest snap angle one last time. And since I'm using the integer values as my piece attribute, I have to go ahead and promote it to the integer. You can see these are floats. I go ahead and angle is being promoted to the integer. And we have set up these corners. So let's actually go ahead and create our snap angle to something like a 5 degrees. So you can see that I have piece for incrementing 5 degrees. You can see that this offset that this piece has to make is more and more when the angle actually is bigger. The bigger the angle, the more I have to offset the geometry to match the curvature, so that this pipe's exit aligns with the next polycurve. So this is one thing that we can either do it automatically or we can do it manually. This offset has to be set along the z-axis of the instance geometry. So you can see that inside here, my offset is more and more on the z-axis as the bigger the angle has become. To showcase, let me go ahead and maybe go to this maybe like 45 degrees. At the 45 degrees, we have this pipe. So by default, it's going to have no offset. It's just going to be on the positive z-axis. We blast the in and out of the pipe. We get our connectivity, add normal, extract its own centroid for each one of these pieces, and we are drawing out the polyline on both of these. We are drawing out a polyline from both of these. So you can see the polyline from the input is in straight line on the positive z-axis, but since this is a 45 degree pipe, the output of it is in a 45 degrees based on relative to the input, like that. And we're getting the intersection point, and we are setting the attribute neck offset from the distance between input and, so basically this point that it has intersected with. We have calculated the distance between the input point to that intersection and output point to that intersection, and we are setting it as an offset for this geometry. So the offset would be the input offset, and the next offset would be the output offset for the next point along the polycurve. And we are doing it for all of these geometry. You can see that if the angle is even bigger, the offset is more and more. So this is how the offset is created. So this basically takes care of the instancing geometry along the curves with this offset, as you can see. But one thing that we have not yet created is our rest of the geometry on straight edges. So what we want to do is basically cut up our current curve to something that looks like, so this should be to something like this. So you can see that the curve has been cut up to accommodate the instance geometry corners, and we only start the pieces only where we know that the instance geometry is not going to be. And this is where the offset attribute that we set up comes in handy. So the big picture is that we go ahead and transfer the offset amount for each point that we need to do an offset on. And then we go ahead and do a for each loop for this curve. So we're doing a for each. So we're using for each piece, which is basically for each primitive. And for each primitive, what we're doing here is we are moving every point by the backwards and forwards attribute. So the next offset and offset is being used as to move these points along its normal and up vector. And then what we're doing is creating a new point. So you can see in this attribute wrangle, what we're doing is we are creating new points at these points that we have offsetted. You can see that here, and these points are going to be match the input and output of the curve. So we have this. It's hard to see, but we have points here, basically at input and output of this geometry. And then we have to just do an add. So here you can see that now we have the same polycurve, only with the straight piece coming only with the points between the ends and starts of the pipes. And then we just do some splitting and merging to make sure that we always get these line segments. We do some checks, and this is this was the setup for the making sure that the polycurves indexes for the primitives are correct. So this is no longer needed from my tests, but this is still a cool way to preserve the point and primitive order, so which I'm probably going to make a video on. So I'm going to leave it. So if you are downloading this zip file, you can look up on the implementation how to retain the primitive order, and then I want to go ahead and instantiate new points on it. So this will look something like this. What we're basically doing is getting our instance geometry. In this case, it's just a simple pipe. We are getting its bounding box, and we calculate how many times it can fit on this curve. So we are doing this for each primitive. We are first of all we are go ahead and translate it. We translate this curve back to face the positive z-axis. So this is going to make calculations a lot easier for us. So basically we take the curve, which can be anywhere in the world, we move it back to the grid positive z direction, we calculate its length, we go ahead and do some calculation how many points can fit there, and do some scaling, and basically move these points back. And once you have instantiated, you can see that it's going to work really nicely. And once we have merged this all together, the tool looks correctly. So the scale attribute is very, very important for this part. So we're not scaling the corners, but since we do not want to move polycurves to match so we don't want to change the length of the curve that we have created too much. So that's why we are scaling the straight pieces by a correct amount to make sure that the scale, make sure that the end and start and all of these points do not change length of the straight pieces drastically. You can see it works really nicely and it's very fast. So I hope you got something from this video to see kind of a big picture how the tool works. So there's still a little bit to do with it, and I need to kind of package it up with the documentation, all of that. But I definitely think this is something very cool to have, and if you want to get this zip file, you can go ahead and download it and explore it and use it. Hope you've learned something, and see you next time.